Good evening everyone, good evening. I welcome you all again to the V.O.T.E Enthuse. Hope you guys are doing great, having the good time at home. Well guys, let me know in the chat box if I'm audible and visible to everyone. Let me know in the chat box, with the thumbs ups. Let me know in the chat box if I'm audible and visible to everyone. Let me know. Hello Banu Prakash. Hello Abhishek. Hi Surya. Hi Nirmal. What's up guys? Long time, yeah? Perfect guys, perfect. So as you all must be knowing, today it's going to be a special session on thermodynamics and thermochemistry. Well guys, it's going to be a very quick revision on the theoretical part of the thermodynamics and the thermochemistry, right? And this session is going to be beneficial for the ones who have watched all the video lectures of the chapter thermodynamics. If you have not watched it yet, go to the playlist, open the thermodynamic chapter, watch the entire video lectures, then go through this session, yeah? Perfect guys. So before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Okay. Hello Vignesh, how are you? Saurabh, there was some mic issue in the last session. That's why I had to end the discussion, yeah? Well, Fahim, the Josh is always high, yeah? It's not the question to be asked. Perfect. Good evening, Fatima. Good evening. Perfect, guys. And I'm damn sure that you guys are super duper excited about the Vedantu Online Talent Examination. Okay, you have got just 6 days to go for the first exam, which is going to be held on 28th of March. That is on Sunday. Well, guys, you can still register for the Vedantu Online Talent Examination. Okay, and the series starts from 28th March till the 18th April. On every Sundays in between 28th March to 18th April, you'll be having the examination, okay? And it's going to be the best thing you can have right now on the online platform. Trust me on that, right? Perfect, guys. For the ones who have not liked the video yet, please do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Perfect guys, perfect. So let me know in the chat box if you guys are super duper excited for the session. Let me know in the chat box. Let me see the Josh of the session first, then I'll be starting. Yes. And people, as I told you, this is the very quick recap of the chapter thermodynamics. I'm not going to solve any sort of problem. It's just going to be the theoretical discussion right here. Well, let me know in the chat box if the Josh is actually high, yeah? Perfect. Perfect guys, perfect. Perfect. Exactly guys. Let's get started with the basic terminologies involved in the thermodynamics, yeah? Well guys, the first terminology which is there in the thermodynamics, that's what we call a system, right? And as per its definition is concerned, system, it is that part of the universe which is under thermodynamic investigation, right? That part of the universe which will be under thermodynamic investigation, that's what we call a system. Whatever will be there in the universe except the system, that's something which we call as surroundings. And we know anything which separates system from the surroundings is what we call as boundary, okay? So these are the three basic terminologies which I've mentioned right here. The first thing, that is the system, any part of the universe which will be under thermodynamic investigation, that's what we call a system. Whatever will be there in the universe except the system, that's what we call as surroundings. And anything which separates system from the surroundings, that's what we call as boundary, yeah? The basic three terminologies which I've discussed. Well guys, talking about the types of boundaries, we have got actually 4 types of boundaries in general. The first one is called as a real boundary. Any wall, any boundary which you can see by your eyes that it's separating system from the surroundings, that's what we call as the real boundary. Yes. Talking about the imaginary one, any boundary which you actually cannot see by your eyes that it is separating system from the surroundings, that's what we call as the imaginary boundary. Talking about the diathermic boundary is the one which allows the passage of heat either from system to surroundings or from surrounding to system, yeah? And what about the adiabatic boundary? Adiabatic boundary is the one which does not allow the passage of heat either from system to surroundings or from surrounding to system, yeah? So we have got 4 different types of general boundaries over here in thermodynamics. Real boundary, which you can see by your eyes. Imaginary one, which you cannot see by your eyes. Diathermic, which allows the passage of heat either from system to surroundings or from surrounding to system. And the adiabatic one, which does not allow the passage of heat either from system to surroundings or from surrounding to system, yeah? Perfect. Talking about the types of system. Well guys, we have got three different types of system in thermodynamics. The first one, which is what we call as open system, then we have got closed system, and at the end we have got isolated system, right? Well, open system is the one which allows the transfer of energy as well as matter with the surroundings. Yeah? Any system which allows the transfer of energy as well as matter with the surroundings, that's what we call as open system. Closed system is the one which allows the transfer of energy only and not the matter. An isolated system is the one which does not allow the exchange of transfer of energy either from system to surroundings or from surrounding to system, right? Isolated system is the one which neither allows energy nor the matter, which neither allows the exchange of energy nor the matter with the surroundings, right? These are the three different types of system which we have right here, okay? Talking about something called as extensive and intensive properties. What are extensive and intensive properties all about? Very simple, guys. Extensive properties are the ones, these are the properties of the system whose value changes on changing the size of the system. Or I can say it in other words as well. Extensive properties are the ones whose value changes on changing the amount of substance present in the system, right? Similarly, intensive properties are the ones whose value do not change on changing the size of the system or on changing the amount of substance present in it. Yes. What are the examples of extensive and intensive properties? Well, guys, extensive properties has got many examples, even intensive properties have got many examples, right? Well, when you talk about moles, when you talk about internal energy, when you talk about enthalpy, Gibbs free energy, entropy, all these are basically the examples of the extensive properties, right? Talking about the intensive properties, their examples, let me tell you, whenever you talk about pressure of the system, whenever you talk about temperature, whenever you talk about specific heat capacity, molar heat capacity, EMF of the cell, concentration, pH, everything over here, we have got intensive property, okay? All those are the examples of the intensive properties. Well, I have got some extensive and intensive properties right here for you on the screen. You can take a screenshot, and anyways, afterwards, once the session ends, you are going to get the PDF of this session in the Telegram group as well as in the description box, okay? Perfect. Wonderful. Let's move on to something called as the important features of extensive properties and intensive properties, okay? Well, guys, let me tell you the first important feature about the extensive property is extensive properties are additive in nature. We can directly add or subtract extensive properties, yeah? Whereas intensive properties, we cannot add or subtract them directly, yeah? This is the first important point which you need to remember. First thing, extensive properties are additive in nature, whereas intensive properties are non-additive in nature. Right? Talking about the second thing, division of two extensive properties, it always becomes intensive. Yeah? Whenever we divide two extensive properties, and whatever property we get on dividing two extensive properties, that new property which we get on dividing the two extensive properties, that's always intensive. Yeah? Similarly, whenever the extensive property is expressed either per unit mass or per unit volume or per unit mole, the new property which comes to us, that's something which we call as intensive property, yeah? For example, if I talk about the extensive property, your heat capacity, yeah? Heat capacity is nothing, it is just the extensive property. When I express the heat capacity per unit mass, it becomes specific heat capacity, and we know specific heat capacity is the intensive property, yeah? Whenever I express the extensive property like heat capacity per unit mole, the new property which comes to us, that's what we call as molar heat capacity. And let me tell you, molar heat capacity is the intensive property. So remember, whenever extensive property is expressed either per unit mass, per unit mole, or per unit volume, the new property which comes to us, that's what we call as intensive property, yeah? Right? Perfect. Let's move on to something called as state parameters or state variables, right? Well, guys, talking about the state parameters are the ones which actually define the state of the system, right? State parameters, these are the variables, these are the parameters which actually define the state of the system. For example, pressure, volume, temperature, moles, these are some parameters which actually define a specific state of the system, right? Perfect. Well, guys, you would have heard about something called as state functions. What are state functions all about? State functions are the ones which are path independent, right? State functions are the ones which only depend on initial and final state of the system. Well, guys, we cannot calculate the absolute value of a state function. we always calculate change in the value of state function, and that change in the value of state function is always equal to final value of state function minus initial value of state function. And moreover, you have got the examples of the state functions as internal energy, enthalpy, Gibbs free energy, right? All these are the examples of the state function. So in short, what I want you guys to remember right now, the definition of the state function, okay? These are something which are path independent. They just depend on initial and final state of the system. We cannot calculate the absolute value of a state function. Therefore, we always calculate change in the value of state function, right? And that change in the value of state function is represented by delta of state function, which I've already mentioned over here for you. Delta of state function is equal to state function की final value minus state function initial value, right? Perfect. And these are the examples which you need to remember about it. Well, talking about the path functions as its name is concerned, okay, path functions are the ones which are path dependent, okay? Heat and work are the examples of the path functions, right? They are actually path dependent quantities, right? Well, you would have heard about something called a cyclic process, and cyclic process is the one in which the system returns to its initial state after going through a lot of steps, right? Whenever a system returns to its initial state after going through a lot of steps, that process is something which we call as cyclic process, yeah? Well guys, in the cyclic process, the initial and final state of the system is same always, yeah? So I can say change in the value of any state function for a cyclic process is always taken to be 0, right? Yeah? Change in the value of any state function for a cyclic process is always taken to be 0, right? Let me know in the chat box if everything is clear till here or not. Let me know in the chat box. Let me look at your chats first. Let me know in the chat box with the thumbs up if everything is damn clear till here. Till then, I can have some water, yeah? Perfect. As I told you guys, this is a quick recap of thermodynamics, right? I'm not going to do any sort of problem right here. This is just the revision of the things, okay, which you would have skipped sometimes, yeah? Perfect. Perfect, guys. Perfect. Wonderful. Let's move on to something called as path functions. This is something which I told you. These are something which are path independent. Examples are heat and work, right? Okay. Well, guys, now comes something called as thermodynamic process. What is thermodynamic process all about, right? Well, let me tell you, the path followed to change the state of the system is something which we call as thermodynamic process. The definition looks strange, yeah? Isn't it? Right? But let me make you understand a bit in detail what is this thermodynamic process all about. Understand, guys, what I'm going to say. Let's say I've got the system right here. I'm taking a container in which I've got the ideal gas right here. And let's assume this ideal gas is present at the initial state. This is the initial state of the ideal gas. And at the initial state of the ideal gas, let's assume the pressure of the ideal gas is P1, the volume of the ideal gas is V1, temperature is T1, and moles are N1, right? Let's assume these are the state parameters which are defining the state of this ideal gas right now. Correct? Now guys, in order to change the state of the system, in order to change the state of this ideal gas, what am I supposed to do? I'm supposed to change the values of these state parameters, yeah? And minimum, if you are going to change one of these parameters right here, the state of the system will automatically get changed, right? Perfect. So people, I'm going to do one thing. I'm going to change the values of state parameters for the same gas right here. Let's say the final state parameter of the gas is P1, V2, T2 and N2. These are the final state parameters of the gas which define the final state of the system, right? This is the final state, this was initial state, and this is the final state of the system. Yeah? So people, understand, when I change the state of the system, what did I exactly do? When I change the state of the system, I actually changed the state parameter volume from V1 to V2, temperature I changed from T1 to T2, number of moles I changed from N1 to N2. Well people, there is something to notice over here, which I'm sure you would have noticed, right? What is that going to be? The initial pressure of the system was P1 and even the final pressure of the system was P1, right? Well guys, I changed the state of the system keeping the pressure constant. I didn't change the pressure, but eventually I changed the state of the system keeping pressure constant. Right? I would have changed the state of the system keeping volume constant. I would have changed the state of the system keeping temperature constant. So basically, what do I have? I've got many paths available for me to change the state of the system. And whatever path I'm following to change the state of the system, that path followed to change the state of the system is something which we call as thermodynamic process. Yeah? Perfect. Well, guys, you have got different types of thermodynamic processes, as you would have heard, right? As you would have discussed. We have already discussed that on the same channel. I hope you remember. Well, the first process, that's something which we call as isochoric process. Any process in which the volume of the system does not change. Any process in which the volume of the system does not change. That's what we call as isochoric process, yeah. Similarly, talking about isobaric process in which the pressure of the system remains unchanged. Okay, whenever I change the state of the system, whenever I'm going to change the state of the system, keeping pressure of the system constant, we call that process isobaric process. Similarly, talking about the isothermal one, whenever the state of the system changes, keeping the temperature constant, we call that process as the isothermal process, yeah. And at the same time, talking about the adiabatic process, whenever you will have a process in which there will be no heat exchange between system and surroundings, that's something which we call as adiabatic process, right? Well, this was something about this was just the introduction of the thermodynamic processes, right? So the first process which we have, that's isochoric, then isobaric, then you have got isothermal, and at the end you have got adiabatic, right? Well, guys, let's try to draw the curves for them. Yes. Well, isochoric process is the one in which the volume of the system remains unchanged. So this curve right here is what we call as isochore, okay, since the volume of the system is not changing at all, right? Well, at the same time, talking about something called as isobaric process. Isobaric process is the one in which the pressure of the system remains unchanged. So this is something which I call as isobar. Well, guys, we have got two more things right here. What are those things going to be? One is called as isothermal, another one is called as adiabatic, right? Well, guys, if I talk about the equation of state of the isothermal process, it's going to be equal to P is equal to K by V. This is something which we call as equation of state for isothermal process, yeah? This is called as equation of state for the isothermal process, where you can see right here in case of isothermal process, well, the pressure and the volume of the system, they are inversely proportional to each other, and whenever we need to plot a curve between two variables which are inversely proportional to each other, what is the nature of the curve? The nature of the curve is something which we call as rectangular hyperbola. And people, this is the curve which is what we call as isotherm right here. Yeah, this is something which we call as isotherm. Well, talking about the adiabatic process, well, the equation of state for the reversible adiabatic process, that's going to be PV raised power gamma is equal to constant. So you can say P is equal to K divided by V to the power gamma. Again, we have got two variables, pressure and volume, and both the ones are inversely proportional to each other. And we know whenever we have got two variables which are inversely proportional to each other, we call the curve again as rectangular hyperbola, right? So this curve right here is something which we call as adiabat, right? Well, guys, you would have noticed one strange thing right here. The nature of P versus V curve for isothermal process, it came out to be hyperbola. At the same time, the nature of P versus V curve for adiabatic process, again it's coming as hyperbola. Now the point is, if I'll be having a single coordinate system like this is pressure, this is volume, and on this we have got two curves like this. On this we have got two curves like this, and the arrow is towards right. And you are going to check which represents the isothermal one, which represents the adiabatic one. Well, let me tell you a simple trick by means of which you can identify which one is the isothermal and which one is the adiabatic, right? Let's get to know that. Understand. Well, guys, I'm going to place the thumb on the common point. Now I'm going to curl my fingers in the clockwise direction. Yes, that curve which touches the fingers first, that's always going to be your isotherm, right? So people, let me tell you, this is your isotherm, and the one that is going to be below it, that's going to be your adiabat, right? So you just got to know which one is the isotherm, which one is the adiabat, right? And at the same time, if I'll plot one more curve like this, understand properly what I'm going to say. See, guys, this is something which is pressure axis, this is the volume axis. Now again I'm going to plot two curves like this. These are again the hyperbolas, and the arrow is towards left, right? Arrow is towards left. Well, people, again you are going to place the thumb on the common point. You are going to curl your fingers in the clockwise direction. Whatever curve is going to touch your fingers first, that's going to be your isotherm, right? So this is again which I call as isotherm, and this is something which I call as adiabat right here. Yeah, so this is how you just check which curve is the isotherm and which curve is the adiabat, right? Well, people, at the same time, I want you guys to remember one more important thing. What is that going to be? That is going to be one common statement. I hope you have derived that. I have derived that on the same channel in the actual thermodynamics session. Okay, well, that's going to be slope of adiabatic curve is always gamma times slope of isothermal curve. I hope you remember that. Or I can say something like this: slope of adiabatic curve is gamma times more than that of slope of isothermal curve. Remember this statement as well. It's very simple, okay? Yeah, perfect. Let's move on to something called as heat. What is heat and what is work? Both the heat and work, these are the modes of transfer of energy between system and surroundings, yeah? Well guys, I'm not supposed to talk in Hindi. This is the English channel, right? This is particularly for the ones who cannot understand Hindi, yeah? That's why I'm talking in English. Otherwise, मैं हिंदी में ही actually पढ़ाता हूँ, ठीक है? Right. Perfect. Talking about something called as heat. What is heat? Heat is nothing, it is just the mode of transfer of energy, right? Whenever energy is to be transferred, energy is to be exchanged between system and surroundings. Whenever energy is to be exchanged between system and surroundings, system and surroundings, they can exchange energy either in the form of heat or in the form of work, right? So both heat and work, these are first of all the path functions, and at the same time, both heat and work, these are the modes of transfer of energy, right? Talking about this heat right here. Heat flows due to the temperature difference, right? There is something which is interesting and which you need to take a note of, okay? What is that? That is the sign conventions of chemistry for the heat and work. Let me tell you, whenever system absorbs heat, Q value is taken to be positive, and whenever system releases heat, Q value is taken to be negative. This is something which I want you guys to take a note of, yeah? Whenever system absorbs heat, Q value is taken to be positive, and whenever system releases heat, Q value is taken to be negative as per the sign conventions right here. Similarly, guys, there is one more path function that's called as work. Work is again the mode of transfer of energy. Whenever energy is to be transferred between system and surroundings, you can do that in the form of work as well, right? System can exchange energy with the surroundings in the form of work. Yeah? And remember, whenever there is the expansion of gas, let's say I've got the system as the ideal gas and the system is expanding, the volume of the gas is increasing. Whenever there is expansion, we always say work is done by the gas, and whenever work is done by the gas, W value is to be taken as negative in chemistry, right? In physics, you take opposite of it, yeah? Right? Similarly, whenever the ideal gas undergoes compression, let's say I'm taking my system as the ideal gas, right? And whenever the gas undergoes compression, what do we say? We say work is done on the system and W value is taken to be positive, yeah? These are the two things which I want you guys to take a note of, right? Right? Perfect. Let's move on, guys. This is something which I told you, when to take Q value positive, when to take Q value negative. Again, talking about work. Well, I told you, whenever there is expansion, work is done by the system, W value negative. Whenever there is compression, work is done on the system, W value is taken to be positive, right? Well, guys, one more important thing. How do we calculate this work? I'm going to give you the general expression to calculate work, okay? Well, I'm giving you the general expression that's going to be minus integral from initial volume of the system to final volume of the system. This is something called as P external multiplied by dV, right? External pressure multiplied by dV, right? Well, guys, we have talked about two processes, if you remember. One is something called as reversible process, one is called as irreversible process, right? I hope you remember, in case of reversible processes, system and surroundings are always almost in equilibrium with each other, or we say P gas is almost equal to P external. Whereas in case of irreversible processes, external pressure is kept constant, right? External pressure is kept constant, okay? Now, guys, understand one important thing right here. What is that going to be? See, if P gas is equal to P external, how do I calculate work done in reversible process then? It's going to be minus integral V1 to V2. Instead of this P external, I'm going to replace it by P gas multiplied by dV, right? This is the general expression to calculate work in reversible process. Similarly, in case of irreversible process, how do we calculate work? Well, guys, I told you, in case of irreversible processes, external pressure is kept constant. Just take this P external out. It's going to be W irreversible is equal to minus P external. Integral of dV is V. Give the upper limit, lower limit. It's going to be minus P external V2 minus V1, or you can write it in the form of W irreversible as minus P external delta V, right? Right? Perfect. Let's move on. This is something which I told you. Whenever there is expansion, work is done by the system or by the gas. Similarly, whenever there is compression, work is done on the system, right? W value is taken to be positive, and whenever P gas is equal to P external, there will be no movement of the piston, there will be no work at that time. This case is going to be isochoric, yeah? Perfect. This is the expression which I gave you just 5 minutes back. Well, guys, well. This is something called as units of energy, okay? This plays an important role in the questions. right? So people, take a note of all these, take a note of all these. SI unit of energy is joule, CGS unit is erg, 1 joule is 10 power 7 ergs. Its another units are ATM liter, bar liter, calories, and people, at the same time, 1 ATM liter is 101.3 joules, 1 bar liter is equal to 100 joules, 1 calorie is 4.2 joules, and 1 ATM liter is 24.2 calories. Take a note of this as well, which is very important, okay? Well, talking about something called as internal energy. How do we define the term internal energy? Well, guys, internal energy is nothing. It is the sum total of all the energies present in the system when the system is at rest, okay? Right? For example, understand. Just a second, guys. See, guys, this is the container right here, and the container is at rest, okay? This is the ideal gas right here in the container, and I'm considering this ideal gas as the system, right? This ideal gas, it possesses different types of energies, and if I take the sum total of all the energies possessed by this ideal gas, the sum total of all the energies possessed by the ideal gas when this container will be at rest, that's what we call as internal energy, right? Well, guys, internal energy is an extensive property, okay? Its value changes on changing the amount of substance present in the system, and at the same time, it's a state function, right? If it is a state function, can we calculate its absolute value? No way. We cannot calculate its absolute value. We always calculate change in the value of state function, yeah? We always calculate change in the value of internal energy, right? Well, guys, one more thing, talking about cyclic process. If for a cyclic process, I need to calculate total change in internal energy, the net change in internal energy, that's going to be 0, because in the cyclic process, initial state of the system will be equal to the final state. So the initial value of internal energy will be equal to the final value of internal energy. So I can say delta U for a cyclic process will be definitely equal to 0, yeah? Similarly, guys, okay, there is one important thing which you need to remember about internal energy. What is that going to be? Internal energy, it depends on actually volume and temperature. For a real gas, internal energy is the function of volume and temperature, I must say. On changing the temperature or on changing the volume of the real gas, its internal energy changes, right? But for the ideal gas, internal energy is the only function of temperature. On changing the temperature, internal energy of the ideal gas changes, right? Well, guys, I'm going to give you one general expression to calculate change in internal energy for the ideal gas. That's going to be delta U is equal to NCV delta T, right? That is the general expression to calculate the internal energy change for the ideal gas whose temperature changes from T1 to T2, for example, right? Well, guys, at the same time, understand, if I'll be having an isothermal process, or before talking about that, let me write the expression for you guys. Delta U is equal to NCV delta T, right? This is valid for the ideal gases. Right? Well, guys, for the isothermal process, we say temperature of the system is constant, right? Whenever the ideal gas undergoes isothermal process, we say temperature of the system is constant. If temperature is constant, I can say delta T is 0. And if the delta T is 0, I'll say delta U for the ideal gas undergoing the isothermal process, that's going to be 0, absolutely, right? One more thing, guys, if during the process delta U for the system comes out to be negative, what does that mean? If the delta U comes out to be negative for the system, I can say temperature of the system will be decreasing with time, right? Similarly, if during the process delta U for the system comes out to be greater than 0, I can simply say temperature of the system will increase with time, right? Okay, this is something which you all must be knowing, I'm sure about that. Well, talking about something called as heat capacity. What is heat capacity all about? Heat capacity is nothing. The amount of heat which is required to raise the temperature of a given substance, the amount of heat which is required to raise the temperature of a given mass of substance by 1 degree centigrade. That's what we call as heat capacity, right? Similarly, let me tell you, it's an extensive property. This heat capacity, which is represented by C, it is an extensive property, right? And people, at the same time, there is something called as specific heat capacity. What is specific heat capacity all about? The heat required, the amount of heat which is required to raise the temperature of a unit mass of a substance by 1 degree. That's what we call a specific heat capacity. And let me tell you, this specific heat capacity, it's an intensive property, yeah? And people, at the same time, there is something called as molar heat capacity. How do we define the molar heat capacity? Molar heat capacity is nothing. It is just the heat energy required to increase the temperature of 1 mole of a substance by 1 degree centigrade, right? Yes. It's okay, Ganesh. This is a revision series, right? This is just the revision of the theory part of the thermodynamics, right? You don't like me. You don't like me to go fast, right? You don't want me to go fast. Yes, Abid, I'll be taking the class on NEET Elite tonight, right? Yes, I'll be doing that. I'll be taking the session on NEET Elite at 11 p.m. And tonight we are going to talk about something called as hyperconjugation, yeah? Okay. All right. Perfect. Right? Now, guys, understand one more thing. I have written something as QE right here. What is QE all about? QE is something called as heat exchanged between system and surroundings when the system is kept at constant volume. Yeah. And let me tell you, heat exchange between system and surroundings at constant volume is always equal to the value of delta U, and that delta U is equal to NCV delta T, right? Similarly, the heat exchanged between system and surroundings kept at constant pressure, that's actually equal to the value of delta H. And what is delta H? That's equal to NCP delta T. That's what we call as change in enthalpy, right? Right. Perfect, guys. Perfect. Akash, this is the English channel. I'm not supposed to talk in Hindi, bro. I'm really sorry. Well, guys, I'm sure you would have heard about these relations as well. For 1 mole of ideal gas, Cp minus Cv is always taken to be R. Yes. For n moles of ideal gas, Cp minus Cv is equal to Nr, right? Right. Well, at the same time, talking about the Cv and Cp values for monoatomic, diatomic, and different gases, right? Let me tell you, the value of Cv for the monoatomic gas, it is equal to 3 by 2R. For the diatomic gas, it's going to be 5 divided by 2R, and gamma value for the monoatomic gas, it's Cp by Cv, it's going to be 5 divided by 3, right? At the same time, if I talk about the diatomic gas or triatomic linear gas, Cv value is nothing. Cv value is going to be 5 divided by 2R, Cp value is going to be 7 divided by 2R, and gamma value is going to be 7 divided by 5, yeah? Similarly, in case of the polyatomic gases, polyatomic non-linear gases, what it's going to be? Cv value is going to be 3R, Cp value is going to be 4R, and gamma value is going to be 4 divided by 3. Well, guys, if you can notice one important thing right here, 5 by 3 value comes out to be 1.66, 7 by 5 value comes out to be 1.4, and 4 by 3 comes out to be 1.33. Well, I can generalize one important statement right here. What is that statement going to be? Understand. I can say something like this. As the atomicity of the gas increases, see, I started with something as monoatomic, then I talked about diatomic, then I talked about polyatomic, right? As the atomicity of the gas increases, the value of gamma decreases, yeah? Prashant, I'm wearing full sweater because, bro, I'm right now live from something called as Kashmir, okay? And over here, temperature right now is, it'll be 1 or 2 degrees centigrade, right? I hope you know that. Perfect, guys. So I want you guys to take a note of all these things. These are going to be highly beneficial for you in the questions, yeah? Right? Perfect. All right. Now, guys, the point is, how do we calculate the molar heat capacity at constant volume for a mixture of gas? Whenever I'll be having mixture of 2 or more chemically non-reacting gases, how do we calculate the Cv value for that mixture, right? There's one simple formula in order to calculate the Cv value for a mixture of gas, right? Which I call a Cv mixture, okay? What is that going to be? Say, for example, I've got 2 or more than 2 gases right here in the container. I'm representing those gases as gas 1, gas 2, and gas 3, yeah? Let's say molar heat capacity of the gas 1 is represented by Cv1, this is Cv2, and this is Cv3. Let's say number of moles of gas 1 in the container is N1, N2, and N3. Well, people, if I want to calculate the molar heat capacity at constant volume for the mixture of gas, it's going to be equal to N1 Cv1 plus N2 Cv2 plus N3 Cv3 divided by what? Divided by N1 plus N2 plus dash dash dash. How many gases will be there, right? This is something by means of which we calculate the molar heat capacity at constant volume for the mixture of gases, yeah? And at the same time, if I need to calculate the Cp for the mixture, molar heat capacity at constant pressure for the mixture of gas, it is simply going to be Cp mixture minus Cv mixture. It is going to be equal to R, as I have given you the formula. Once I get the Cv mixture, I can write Cp mixture is going to be R plus Cv mixture. And people, at the same time, I can calculate gamma for the mixture. It's going to be equal to Cp mixture divided by what? Divided by Cv mixture, right? This is something which you would have already known, right? I'm sure about that. Okay, Perfect, guys. Perfect, perfect, perfect. Now talking about something called as first law of thermodynamics. What is first law of thermodynamics all about? Well, let me tell you, this first law of thermodynamics, it is basically the energy conservation principle, number one. Okay? And as per your first law of thermodynamics, when the state of the system changes, there is change in the internal energy of the system. And that change in the internal energy of the system can be brought about in two ways. Number one, when heat is absorbed or released by the system. Number two, when work is done on the system or by the system. Okay, let me explain it again for you. It is basically the energy conservation principle, and as per your FLTD, first law of thermodynamics, is concerned, let me tell you, when the state of the system changes, there is change in the internal energy of the system. Okay, and that change in the internal energy of the system can be brought about in two ways. Number one, when heat is absorbed or released by the system. Number two, when work is done by the system or on the system, right? And talking about the mathematical statement of the first law of thermodynamics, it's going to be like this. I hope you know that delta U is equal to Q plus W. Well, people, when we use this expression, you need to be careful with only the sign conventions, yeah? What is Q? Q is nothing. Q is the heat energy absorbed or released by the system. What is W? W is the work done either by the system or on the system, right? Okay, you need to be careful with the sign conventions. Whenever system absorbs heat, Q value is taken to be positive. Whenever system releases heat, Q value is taken to be negative. Whenever there is expansion, work is done by the system, W value negative. Whenever there is compression, work is done on the system, W value is taken to be positive. That's something which you need to have a look on, yeah? Perfect. Perfect, guys. Talking about something called as the units of pressure and volume. Okay, these are the different units of pressure, volume, and the gas constant which you need to know, because in the problems you might get stuck. Okay, you might get stuck on converting the units of pressure and all. That's why I have come up with all these units right here for you. You can take the screenshot as well, or else you'll be getting the PDF in the Telegram group as well. So no need to worry about that. Yeah. Perfect, guys. I'm changing the slide. Let's talk about something called as enthalpy change. Okay, how do we define enthalpy change? Enthalpy change, delta H. How do we define that? Enthalpy change is basically the heat exchanged between system and surroundings at constant pressure, right? Heat exchanged between system and surroundings at constant pressure is something which we call as enthalpy change, right? And people, there is a simple formula to calculate delta H. That's going to be NCP delta T, right? I hope you know that. And based on the sign of delta H, if the delta H for the process comes out to be positive, we say that process endothermic. If the value of delta H for the process comes out to be negative, we say that process exothermic, right? That's something which I want you guys to take a note of. And at the same time, the enthalpy, it's a state function, okay? It's path independent. Its value only depends on initial and final state of the system. We cannot calculate its absolute value. Okay, therefore we always calculate change in the value of enthalpy, which is delta H, which is going to be H final minus H initial. Yeah, I hope you know that. We have talked about that in detail. I hope you remember. Right? So enthalpy function. I mean, how do we define enthalpy change? First of all, enthalpy change is the heat energy exchanged between system and surroundings at constant pressure. Number one, it is a state function. It is an extensive property. For a cyclic process, delta H is 0. For a cyclic process, the delta H net is going to be 0. Okay, and how do we calculate delta H for an ideal gas? It's going to be equal to NCP, delta H is equal to NCP delta T. And based on the sign of delta H, we classify processes into two types. One is called as endo, one is called as exo. Endothermic processes are the ones for which delta H value comes out to be positive, and exothermic processes are the ones for which delta H value comes out to be negative, right? This is something which I want you guys to take a note of, correct? Just a second, guys. Perfect. Now talking about something called as relation between delta H and delta U. What is the relation between enthalpy change and the internal energy change? Well, guys, I'm going to give you one general result which can use anywhere, okay, in order to calculate the relation between delta H and delta U. Well, guys, I'm writing something like this. Delta H is equal delta U plus delta of PV. This is one general result which you can use in order to calculate the enthalpy change or internal energy change. That's it, right? Okay, and people, there are few things which you need to take a note of right here. What are those things going to be? Let me tell you. If pressure of the system comes out to be constant, if the pressure of the system was constant, then you can modify the equation as delta H is equal delta U plus P delta V. If volume of the system is constant, then you can write something as delta H is equal to delta U plus V delta P. And people, at the same time, if pressure and volume of the system change simultaneously, I can say delta H is equal to delta U plus P2 V2 minus P1 V1. Yeah, these are the three relations which I want you guys to take a note of. Yeah, this one is valid when the pressure of the system is constant. This one is valid when the volume of the system is kept constant, and this one is valid when pressure and temperature both will be changing simultaneously. Yeah, and people, for the homogeneous gaseous phase reaction carried out at constant temperature, we always say delta H is equal to delta U plus delta NGRT, right? This is the relation which is valid for a homogeneous gaseous phase reaction kept at constant temperature, right? Well, what is this delta Ng all about? What is this delta Ng all about? Delta Ng is nothing. It is number of moles of gaseous products in the reaction minus number of moles of gaseous reactants. That's it, right? Prashant, you can go to the thermodynamics actual sessions which I've taken. I've taken around 10 sessions on thermodynamics, and I've taught a lot about thermodynamics in detail. You can just go to the playlist, watch the video lectures of this. This is just the revision of whatever we have discussed. That's it, right? This is just a quick revision. That's why I'm a bit fast. Okay? Hi Danish, how are you doing? Yes, Rahila, you can do that. You can do that. You can do that. Thank you, Harshit. Thank you so much. Perfect, guys. Perfect. Well. There is something called as reversible and irreversible process. Okay. How do we differentiate the two? Okay. How do we differentiate the two? Reversible processes are the ones in which system and surroundings will be in equilibrium with each other, right? Okay. Or I can say, in case of reversible processes, driving force will be greater than the opposing force only by a small amount, right? These reversible processes, these are actually the imaginary processes, okay? Okay, and at the same time, how do we calculate work in case of reversible processes? I told you a few minutes back, W is equal to minus integral V1 to V2 P gas multiplied by dV, right? Right? Well, antimony scored, it's going to be, I guess, 7K something. Yeah, after using the coupon code WSCC. Okay. Similarly, guys, talking about irreversible processes are the ones in which external pressure is kept constant. Okay, these are very fast processes. In case of irreversible processes, I can say something as driving force is far greater than the opposing force. Yeah, and these are actually the real processes in which, how do we calculate work? In which we calculate work by the formula minus P external delta V. Okay, this is something which I told you a few minutes back when I taught you work. Yeah, perfect. Okay, guys, understand. Just a second. Okay, talking about something called as isochoric process. What is isochoric process all about? As I told you a few minutes back, isochoric process is the one in which the volume of the system remains constant, volume of the system is kept constant, okay? So work done in case of isochoric process is always taken to be zero. And a few minutes back, I have told you the curve for P versus V for the isochoric process, it's going to be the straight line parallel to the pressure axis, right? And we call that curve as the isochore. I hope you know that as well, right? Similarly, guys, talking about something called as isothermal process. What is isothermal process all about? Few minutes back, I told you, isothermal process is that process in which the temperature of the system is kept constant, right? Any process in which temperature of the system is kept constant, we call that process the isothermal process, right? I hope you know that as well. Well, people, there is something interesting. What is that going to be? See, let's say I've got the ideal gas in the container, yeah? If I'm keeping the ideal gas at constant temperature, can I say its delta U is going to be 0? Absolutely, because temperature is constant. If delta T is 0, I can say delta U is 0. Yeah, perfect. So as per your first law of thermodynamics, delta U is equal to Q plus W. If I apply the first law of thermodynamics for the isothermal processes for which delta U is 0, I can say Q is equal to minus W, right? Well, guys, from here you can generalize two statements. What are the two statements going to be? Let me tell you. Whenever there is isothermal expansion of an ideal gas, heat is always absorbed by the gas, right? And whenever there is isothermal compression of the ideal gas, heat is always released by the gas. So during isothermal expansion of the ideal gas, heat is absorbed by the gas. Similarly, during isothermal compression of the ideal gas, heat is released by the gas, yeah? So remember these things as well. These are going to be very, very useful for you, okay? And for the ideal gas undergoing isothermal process, its delta U as well as delta H is equal to 0, because we know delta U is actually equal to, for the ideal gas, delta U is actually equal to NCV delta T. If delta T is 0, then delta U as well as delta H are going to be 0, because in the formulas of both the ones, you get delta U, delta T, right? Yes. Perfect, perfect. Now the point is, how do we calculate work done in reversible isothermal process? Well, guys, I'm going to give you some results. Okay, so remember these results. I'm not going to derive these. If you want to see the derivation, then go to the actual sessions which I've taken on the thermodynamics. Okay, which you can get on in the playlist. Yeah. Let me right now give you the general expressions by means of which you can calculate the work done in case of reversible isothermal processes. Well, guys, work done in case of reversible isothermal process is simply minus nRT. It's going to be ln V2 divided by V1, or you can write it in terms of pressure as well. It's going to be minus nRT ln P1 divided by P2. These are the two general expressions which you can use in order to calculate work done in case of a reversible isothermal process. Yeah. Similarly, in case of irreversible isothermal process, how do we calculate work? Well, guys, in case of irreversible process, we know W is equal to minus P external delta V, which is going to be V2 minus V1. Yeah, this is one result which you can use in order to calculate work done in case of irreversible isothermal process. Or you can do something like this. You can just change it like this. W irreversible is going to be equal minus P external. Instead of final volume of the system, you can write nRT divided by P2 minus, instead of V1, you can write nRT divided by P1. Now you can do one thing, you can take nRT out, you get the formula as W irreversible is equal to minus P external. It's going to be nRT multiplied by 1 divided by P2 minus 1 divided by P1 right here. Well, guys, these are the two expressions which I want you guys to take a note of in order to calculate work done in irreversible isothermal process. Yeah, so take a note of it. These are going to be very helpful for you in doing these problems, right? Perfect. V Enthusian. Well, bro, I cannot understand the language which you are writing right here. Okay, I have no idea what you're writing. Perfect. All right, talking about something else, adiabatic process. Well, guys, what is adiabatic process all about? What is adiabatic process all about? Adiabatic process is the one in which there is no heat exchange between system and surroundings. Yeah, correct. Q value is 0. Yeah. Now, in case of adiabatic process, how do we calculate work done in case of reversible adiabatic, and how do we calculate work done in case of irreversible adiabatic process? Well, I guess come up with some expressions right here. Yes, the first expression which you are going to remember in order to calculate work done in reversible adiabatic process, that's going to be this expression. W reversible is equal to N CVT2 minus T1. Or you just remember this expression in order to calculate work done in reversible adiabatic process. Yeah. Similarly, I have got two expressions in order to calculate work done in irreversible adiabatic process as well. And what are those expressions going to be? See, first thing, W irreversible, again you can use minus P external V2 minus V1, or this is one more result which you can use in order to calculate work in case of irreversible adiabatic process, which is minus P external NR T2 divided by P2 minus T1 divided by P1, right? So these are two expressions. Again, this is the first one and this is the second one, which you can use in order to calculate work done in irreversible adiabatic process. Yeah. Perfect. Now, people, there is something called as, these are two important statements which I want you guys to take a note of. What are these statements going to be? Say, we know in case of adiabatic process, Q value is 0. Well, guys, if the value of Q is 0, then as per first law of thermodynamics, delta U is equal to W, right? Delta U is equal to W. Yes, absolutely. Well, guys, two things I want you guys to take a note of. What are those two things going to be? Number one, during adiabatic expansion of an ideal gas, temperature of the system decreases. During adiabatic compression of an ideal gas, temperature of the system increases. Okay, or I can generalize it like this. I can say, during adiabatic expansion of an ideal gas, temperature of the system decreases, or I can say cooling of the system occurs. Yeah. Similarly, I can say during adiabatic compression of an ideal gas, I can say temperature of the system increases, or I can say heating of the system occurs. Yeah, these are two important things which I want you guys to take a note of right here. Okay, and I have written these in terms of the mathematical equation. Yeah, you can just follow these as well. Well, guys, talking about something called as the final temperature. How do we calculate final temperature of the system in case of reversible adiabatic process? Well, guys, there are two equations which you can remember in order to calculate the final temperature of the system in case of reversible adiabatic process. The first equation is going to be T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. Okay, the second one is going to be P1 raised power 1 minus gamma, T1 raised power gamma is equal to P2 raised power 1 minus gamma, T2 raised power gamma. Yeah, these are two equations which I want you guys to use in order to calculate final temperature T2 of the system if it is carried out reversibly and adiabatically. Yeah, and at the same time, if the same process is carried out irreversibly. Okay, that means if I'll be having irreversible adiabatic process. In case of irreversible adiabatic process, how do we calculate final temperature? In order to calculate the final temperature, in case of irreversible adiabatic process, what you guys are going to do? You guys are going to going to use the first law of thermodynamics. We know in case of as per the first law is concerned, Q value is 0. Q value is 0 for the adiabatic one, right? If Q value is 0, I can say delta U is equal to W. I've written the same thing, delta U is equal to W. Now guys, this delta U is NC T2 minus T1. This W is minus P external V2 minus V1. So you can just equate these two things. Right here in order to calculate the final temperature of the system. You can just equate these two things in order to calculate final temperature of the system, which is T2 in case of irreversible adiabatic process. Or people, what you can do right here, you can use one more expression, right? What is that going to be? Let me make that for you. See guys, the first expression which you guys are going to use, that's NCV T2 minus T1 is equal to minus P external. It's going to be V2 minus V1. Yeah, this is one expression which you can use in order to calculate final temperature of the system in case of irreversible adiabatic. Yeah, and people, instead of CV, I can write R by gamma minus 1. So it's going to be NR divided by gamma minus 1 multiplied by T2 minus T1 is going to be equal to minus P external. Well, instead of V2, I can write something as NR T2 divided by P2 minus nRT1 divided by P1. Well people, as you have noticed something, NR over here, we have got NR over here, we have got NR over here. Just cancel this NR, you get the result as T2 minus T1 divided by gamma minus 1 is equal to minus P external T2 by P2 minus T1 divided by P1. This is one more result which you can use in order to calculate final temperature in case of irreversible adiabatic process. Yeah, I'm sure this is clear. Perfect. Now guys, the last topic right here, this which is something which we call as free expansion. What is free expansion all about? Just a second guys. Okay, what is free expansion all about? Free expansion is something called as expansion against zero external pressure. Okay, expansion of the gas against zero external pressure is something called as free expansion. Yeah. Okay, and in case of free expansion, let me tell you, free expansion is always irreversible. It is always irreversible, number one. Number two, work done in case of free expansion is taken to be 0. Okay, and at the same time, this free expansion is of two types. One is called as isothermal free expansion. One is called as adiabatic free expansion. Yeah. Well guys, if I talk about the isothermal free expansion of an ideal gas, see, it's the free expansion, so W value is 0, and at the same time it's isothermal, so delta U is 0. If W is 0, delta U is 0, I can say Q is also 0, right? So I can generalize a simple statement right here, an isothermal free expansion of an ideal gas is adiabatic as well. Yeah. Similarly guys, talking about something called as adiabatic free expansion. Since in case of free expansion, W value is 0. Since W is 0, at the same time the process is adiabatic, so Q value is 0. So if Q is 0, W is 0, I can simply generalize a statement delta U is 0, and for which process delta U is 0, that is going to be your isothermal one. Yeah, so I can generalize one more statement right here, an adiabatic free expansion of an ideal gas is isothermal as well. Okay, well guys, well, this was all. I hope most of the things from the dynamics part are cleared. Okay, now I'll come up with one more session from the thermochemistry part. Okay, and in that thermochemistry part we are going to talk about the heats of reactions, entropy and Gibbs free energy, right? So I hope your basic things, this was just a quick revision of the thermodynamics part, and I'm sure this would have been clear to you, right? Perfect. Let me know in the chat box. Well, Azam, I have taught redox titration in detail. You can go to the playlist. You can get the redox chapter. There you can find it, yeah? Perfect, guys. Perfect. Wonderful. So, people, this was all from my side in the tonight's session. I'll see you guys soon with the thermochemistry part, okay? Till then, you guys take care. Bye-bye. God bless you all. And at the end, for the ones who joined us late, well, we have started the JEE 2021 crash course for the ones who are going to appear in the JEE in the April session or in the May attempt. For the ones whose preparation is up to the mark, who just want the brush up the concepts, okay, the crash course is best thing which you can get right here. Okay, and at the same time in the crash course, no need to worry about the test series, no need to worry about the assignments, everything is included there. And let me tell you, I'm going to personally train you for the April attempt as well as for the May attempt, right? Okay, in the crash course, in the JEE 2020 crash course. For that, you need to go to the link which is there in the description box of the video, click on the link, use the code WSCC, and on using the code of WSCC, you'll be getting the 30% off as well. And people, one more important announcement, that is for the V.O.T.E, okay, Vedantu Online Talent Examination, right? And I'm sure all of you must be familiar about that now, because on every channel we have disclosed that Vedantu Online Talent Examination. You can just register, you can just click on the link which is there in the description box of the video. Just click on the link, register for the V.O.T.E and get a lot of surprise in that, right? Perfect. So this was all from my side in the tonight's session. Yeah. So I'll see you guys soon. Till then, you guys take care. Bye-bye. God bless you all and love you all. Stay safe, guys. Bye.